All the presenters, everyone that attends this conference is so friendly, so willing to teach, so willing to learn from you too. So it's not just watching these videos, it's kind of getting that insight afterwards and around at dinner, at drinks, like all the other aspects of the conference besides just like that technical information.
Greetings, everybody. I'm Stephen Brawner. This is robotics at compile time, optimizing robotics algorithms with C++ compile time features. So before I get started, I do want to say thank you to CppCon for even creating a robotics track. Not only am I a first-time presenter, I'm a first-time attendee. So having the robotics track here was the kick in the pants to get me to finally come say hello to you all. A little bit more about me. I'm a robotics software consultant based in Portland, Oregon. I am also the current chief roboticist for Flex Solutions, a robotics startup company. I've worked for several past robotics companies, including Open Robotics, Picnic, Verb Surgical, Magnopus, Format, Amazon, across several different industries, solar technologies, surgical robotics, TV and film included. That is my dog, Taylor, and she currently thinks that I'm holding a treat in this picture. So yesterday I did say, yes, I like puppies, if anybody was at that talk. So in general, I tend to think about software and robotics in kind of two different categories. There's sort of the robot-agnostic software. This is designed to be used across many different types of robots, many different architectures. And in general, it's code that will ingest a plain text file that describes your robot at runtime, but upon startup. So this sort of software requires a lot of runtime decisions. Some examples include like the ROS2 ecosystems, Drake, Ignition, Gazebo, Isaac, Picnic is here, Move It, that sort of thing. Whereas a lot of the software that's written at kind of hardware companies is very targeted to these robots individually, and it's maintained by the people who work at these companies. It can be written with very specific platforms in mind, and so the code is very performant, it runs very well, and this is a sort of approach is generally required for real-time controls. But it takes a lot of money, a lot of development effort. This is why robots cost a lot of money to develop. So thank you, Davide. Yesterday, he reminded me that robotics talks need a robotics video. And so this is my client, Matt. He's demonstrating the Flex robot on the USS Midway down in San Diego. It's this aircraft carrier museum. And we just kind of walked around the ship with their permission, throwing this robot in different places. And the general idea of this robot is to use it for inspection and operation and maintenance purposes. This is inside of a ballast tank. And there's many different applications that we're targeting for something like this. But the idea is there's just a lot of embedded processors on this hardware. Like this hardware is not changing anytime soon. So we can really target the software that we write for this robot. But we do want to write generalizable code so it can be translated across different robots. Okay. So in general, hardware development in robotics, the requirements are well known long ahead of time, like several years in fact. I ran into some people from Boston Dynamics, very nice people here. They announced the Spot robot in 2016, I believe, and Wikipedia tells me that kind of the first release of it was in late 2019. So many, many years to develop software that runs on this robot, and the robot itself did not change. Like these mechanical and electrical designs are locked in years in advance. Your robot's not gonna suddenly start adding limbs or develop new senses after you deploy it. So we can write this software to target very specific board architectures and robot platform designs. And so I did a survey of a lot of the companies that I have worked with. And I would say they generally ship software much more frequently than they ship hardware. For example, they might develop one a year. I think iRobot might get up to that level of production. They do have new models of the Roomba, basically about that cadence. And then I did some super scientific research to figure out, well, how many software builds are there? And I think it's safe to say a lot more. So the goal when I kind of approach writing code like this is to write generalizable software that could be used across many different robots and platforms. But it is as if written specifically for any one individual robot. The zero cost abstractions that I hear a lot around this conference. And I think this is a great use case. So my vision of a robot program kind of looks like this. There is a spec file that describes your robot, and you have your application code that's been unit tested and whatnot, and then you combine it at compile time, and then you can run it. And it takes the hardware specs, and it combines it with your program to write very performant code. So to get into RealTime software, this is, I'm sure all of you kind of know what RealTime software, but just to go over it again, this is deterministic software that can produce the same result for a known input, and it generally delivers the correct result at the correct time, so to say. There's kind of three general classifications of real-time software. These are not by means any strict classification because each organization, each project has its own requirements about this sort of thing. But the classification of hard real-time, where if you miss a deadline in your timing, that's a program fault, the robot stops, it's a very catastrophic situation. Maybe emergency mechanisms have to be deployed to guarantee that your robot's not going to hurt somebody in the surgical robotics case. Then there's kind of the idea of firm real-time, where this is a result that might be treated as worthless. For example, in an assembly line, if you're welding a beam and you miss a deadline and that weld goes out of the path that it's supposed to, well, you can just throw away that beam that you're working on or that steel thing that you're working on. And then there's also the kind of a category of soft real-time where you do want your code to run at real time, but perhaps in audio visual video processing, if it doesn't happen, you get lag, you get buffering, you get some clips in the audio. It's not catastrophic, but it's certainly not desired. So in robotics, I just want to kind of iterate that generally this software, if you write real-time software, it has to run on a real-time operating system or on a bare metal embedded device that can also guarantee kind of real-time properties. And there's kind of a few general concepts we like to avoid in real-time software: dynamic memory allocation, exceptions, device I/O, locking primitives. These kinds of things are not deterministic generally. And when we talk about optimizing code, we talk about optimizing for CPU and memory budgets because these processors were chosen several years beforehand, and so you better make sure that you don't overload your CPU. So why C++ is great for real-time robotics? Every single robotics company I've seen uses C++. And I think it comes down to a lot because C++ is standardized. There is an ISO standard that we can look at and say, yes, this code does exactly what it's going to do because it's standardized, because these compilers have been tested long ahead of time. And then we can add flags like wpedantic to make sure that, yes, this code is conformant. So when the FAA or the FDA or whatever organization asks, how do you know that your robot's not going to hurt somebody? We can, do all this requirements traceability and ensure that, we're avoiding DMA exceptions or DMA exceptions, IO locks. We can pretty much guarantee stuff like that by how we write our code. And then, of course, everybody loves strong type safety in large organizations because it helps you use tooling to validate what your software is actually doing and the possible states it can be in. And we all like C++ because it's performant. There is one point I would say where we could do a little bit better with C++. And I've noticed that several robotics companies will not use the STL because in very safety critical situations, because it's perhaps a little bit underspecified. So if we had something that could standardize guarantees in the STL around DMA and locks and IO about whether they use something. So like briefly, constexpr didn't allow dynamic memory allocation, but perhaps we could add a const mem that ensures that there's a flow down of, this does not dynamically allocate. Or perhaps like no except, there's a no allocate. So we can kind of track that, yes, these things are not happening. And then we can point to the regulators being like, yes, this code does not do this. OK. So to get into, I guess, the compile time optimizations that I've liked to use in some of the robotics code that I use, let me bring it back to kind of this picture where you include your specs and you have your application and you combine them at runtime. Your application knows all these details, and so the compiler can just optimize it. I'll start off with a simple example that is not exactly or specifically robotics related, but maybe is something that generally everybody can understand. So take your classic ring buffer. And if you're going to do kind of a stack allocated version, you have a type name T and the max size. And while the aligned memory part is interesting, I'll point you to this talk I really like by David Stone, How Hard Could Be. That's about static vector. Ring buffer is kind of a similar example. But in this case, I want to draw attention to what happens if type name T is small. What happens if max size is kind of a small size? Well, the overhead in memory of this type is dominated by these head and tail items. So one simple optimization you might do is use a compile time struct looked up to choose the right size type for head and tail such that it's as small as you can actually use. So the smallest size type 4 kind of looks like this. It's a type alias against stood conditional, where if the size of the ring buffer is less than the limits of uint8 max, then we'll choose uint8 max. Otherwise, move on to the next type. If it's small enough for uint16, use uint16. And then if it's small enough to use 32, use 32, otherwise use 64, that kind of thing. So your ring buffer object in space could be, the footprint in memory could be reduced. But going a bit further in our ring buffer example, take a look at pushback. So we all know what this ring buffer should do when the size is less than the max size. We can just store it and then increment our head and continue on. But what happens in the case where you're at your max size? What do you want your ring buffer to do? If you're at runtime, you could throw an exception, but this is real-time software. We do not want to do that sort of thing. And so we want to choose a behavior and kind of stick with it. I don't think returning, true or false in pushback is very helpful because that just propagates your error onward. And so we could add a template type parameter called fill behavior and kind of pass on this behavior to that template type parameter. And you could pass it in into the constructor, so you could do template argument deduction. And so now pushback, we'll just call this fill behavior pushback. And then in that way, if it's going to drop them because you need to make sure you preserve the most, or the first parts of this ring buffer, or if you want to overwrite because you're just continuously going, this just happens. There's no errors, the behavior is expected, and you can just work with this. The one thing I will say, though, is if you're creating kind of a library class like this ring buffer, the possible number of types that fill behavior could be is open. And so users could potentially hang themselves in this scenario because they're allowed to specify fill behavior. So the guarantee of the ring buffer is dependent on the guarantees provided by the fill buffer. And so for some library types that you add, you might want to restrict the limits of what the user can do. And so in this case, I'm saying, all right, we're going to switch to an enum class, and now you can override ignore. We're going to do a lookup of the fill behavior using that enum class. And then we can just do template specialization to make sure that the behaviors that I wrote are the ones that they're allowed to choose, and they're not really allowed to do much more than that. Okay, so moving on to robotics control. This is why you all came here, right, for the robotics? So going back to the FlexBot, it's kind of my motivating example going forward. So this is a snake-like robot we use for inspection, and the problem that we are going to talk about here is how do you move the robot in Cartesian space with a simple joystick input, and we need a read encoders and write to the motor drivers much greater than 100 hertz. Code is executed on embedded chips with 100 kilobytes of memory, and we need to ensure that there are no self-collisions or control oscillations or dropouts, so that even though this is not used in safety-critical applications, the user who, the technician who uses the robot doesn't just throw it in the trash. So the algorithm I'll talk about first, let's take in forward kinematics. This is the problem of computing the position and orientation of each link on a robot as a function of the robot's joint positions. So link is each rigid component of a robot. Joint is the mechanism between links that kind of generate the motion. So in other terms, like the bones of your arm and like your elbow, the link would be the arm and the joint would be the elbow type of thing. There's several different types of joints. There's a revolute joint in our robot where it'll spin around an axis. There's linear prismatic joints, not exactly as easy to see here, but they'll move in a linear path. And then we also oftentimes use a fixed joint to describe transforms between, say, the camera on the end of the robot and the position relative to another joint. And then each different type of joint here has its own limits. The revolute joint might only be able to spin so much, but there's also infinite possibility. There's also robots with infinite joints where they can just kind of spin continuously. Linear prismatic joints definitely have a strict limit. Otherwise, I don't know. I've never seen a linear prismatic joint that's infinite. These transforms in kinematics are described as geometric transformations, where points in one reference frame can be transformed to points in another reference frame. We generally care about, in these geometric transformations, rotation and translation. And so just a picture of kind of going from one reference frame on your robot to another reference frame on a robot requires a fixed transform and also a changing transform. So that's a function of your joint position. And then the moving from one part of the robot to another part of the robot and getting the transform across the entire robot is just a product of all the different types or all the different transforms along the way. So here's one way you could solve this problem, and I've seen this in code that uses the approach of ingesting text files, where you have to kind of make these decisions at runtime. And so you use a std variant or OOP to represent multiple different types of joints that have like similar interfaces. And for this problem, we're going to use Eigen's isometry 3D, which is a geometric transform that allows rotation and translation. The math guys like to talk about what a transform preserves, but programmers like to talk about what it might change. So I use transform. So for the fixed case, it's very simple. We just need to pass in a transform that is basically the fixed transform from one reference frame to another. And then so if we want to compute the pose of this joint, it's literally just returning fixed. And then like the revolute joint, it also has a fixed transform, And it also it now has an axis for the about what it rotates. And then calling pose takes it a position, and we can use Eigen's angle axis type to compute this rotation. And similarly for prismatic, it takes in a position, and we can use Eigen's translation 3D. So I kind of just want to point out, oh, I gotta extend over here. So Eigen does a great thing where if you kind of compose these different geometric transformation types together, you get kind of really good results. So here we're using the general version of the isometry 3D, and like the amount of assembly that's compiled is fairly large. If we simplify the type to something like quaternions, quaternions is kind of a simple representation of rotation, and if like you'll notice we're now down to like 99 lines of assembly. Kind of the simplest case, of course, is a translation. Like even though this is a transformation type, combining two translations together is really just summing the coordinates of each individual one. So it can get very efficient. And so we want to preserve that utility in our types. Okay. Come back. So yeah, how can we reduce some of that duplication with metaprogramming? We're going to start with an enum class of joint type, fixed, prismatic, revolute. And then now we're going to have a singular template class, joint, and offload this calculation of what that joint or transform should be to a function. And that will take in that joint type as a template type parameter. And then we can do that product. And we can, because we know at compile time what type of joint this is, we can use if constexpr to return the identity for that component of the transform, or the translation 3D if it's prismatic, or the angle axis if it's revolute. And then we can go one step further and take in as a template type parameter that fixed transform, because we might not always want to use a general isometry 3D for that sort of thing. And you would also take that in at compile time, and then you have your calculation down there, and then it can kind of do the right thing and try to optimize some of that. So let's see. Where'd my mouse go? It's over there. So just to kind of compare, so what I've done here is I've added my three classes, fixed, revolute, prismatic. I removed all the dots and filled them in. Joint here is a stood variant of fixed, revolute, prismatic. And then we can run our forward kinematics using some stood algorithms like transform and accumulate. This is kind of happening at runtime, so we have to use stood vectors. We can use spans to see into kind of these other container classes, but we also have a variant which has a lot of kind of runtime. Let's see, let's bring this down. It kind of has a lot of runtime errors that are possible. And like, so you can scroll through this and see that we're not really just doing a lot of the matrix multiplication and vector addition. Like there's, you kind of get down here and there's like variant bad access. There's use of deleters because you're allocating memory. And there's just a lot happening that like we would rather not do during the runtime of a robot, because we know ahead of time how many links there are, how many joints there are. And so we could just remove all that. Or what types of joints they are, or what type of link they are. So let me go back to the next comparison. All right. So kind of my compile time example, this is a function that returns a different angle axis. We have the joint with the two type parameters and calculate pose. And then to kind of make that computation of the forward kinematics, for this example, I used fold expressions. And then for like a simple use case for our flex robot is kind of a 3-joint segment, 1 revolute joint, 1 prismatic joint, and then a second revolute joint. And then, yeah, so running this is simply combining along kind of a fold expression. And what, yeah, else? All right, all right. And with the simple kind of 3-segment case, we've generated less assembly. And then we're just doing multiplication. Or to like, and then what happens when it's the 9 case, which would be like a full robot. What we'll see is it generates more assembly in this version than, I guess, the runtime approach. But what's missing is all those possible error situations that might have come up with our runtime containers. And what happens if the type is not correct, or memory could not be allocated. Like, this is just code that's going to run. And so you can point to your regulator and be like, there's no possible way there can be an error in this code, because these instructions do not have that property along those lines. And then kind of one other type of customization point that we could do with our joint is talking about limits. So kind of want to, the ability to, we're basically gonna sanitize that position with like something like stood clamp or some sort of modulus with offset, or in the case of an infinite joint, just a no-op. And so we want to make that correct choice baked into our code without having to make that choice at runtime, kind of deducing what that should be. And so we'll add in another type parameter, limits, and then we can just overload the call operator to call clamp position. And in that case, we can pass in lambda, that's just a no-op. For wrapped limits, this might use modulo with offset, which is an operation which similar to modulus, but it can also be done at floating point, where basically you are shifting the range. So you could shift like a rotational joint from 0 to 720 to positive or minus like negative 180 sort of thing. And then of course we have the clamp limits. Okay, and then I will move on to my next algorithm. So the next one that I wanted to talk about is collision detection. This is the problem of trying to decide in real time, is a robot colliding with itself? This is not the problem of, or the one I'm talking about is not the problem of trying to decide whether the robot's colliding with environment. For the FlexBot, we figure that's going to happen a lot. And in the surgery case, I believe colliding with your environment is called surgery. So, and each physical link of the robot is represented by one or more collision shapes. And kind of a naive approach might be to do the n-squared combinations, but using a KD tree, you can use an n log n. But in the situation of our flexbot here, I'm not going to write the n log n operation because we just have to compute a few different segments. We can add 3 or 4 more segments, and the number of checks that we have to do will certainly be less than if we did the n log n situation. So we'll represent this as a collision of different shapes that are combined together. You can use simple shapes, you can use meshes, but one thing to point out is that the collision of, say, a cylinder with a box can be just very simple mathematical computations. And so we want to get at those simple calculations as efficiently as possible in our compile time code. So how you might do this with runtime is you'll need kind of a polymorphic shape with pose, and then you have some sort of function that decides whether they collide with one another. But this isn't the end of the story, because you now have to dig into your shape and figure out what type of shape it is and how does it collide with this other type of shape. And the worst place I saw somebody try to do this was with a stood map. I won't name names, but it has happened. And so we want to avoid kind of that runtime decision because this robot is known for so many years ahead of time. And so in our example here in runtime, you might use, oh wait, did I jump forward? No, yes. So I was going to use a ranges example for an upcoming range. We'll need to introduce this tuple of the 2 types of shapes and pull them apart to call is in collision. And then we can use kind of a nice Cartesian product in CppCon23 and figure out, are all these shapes in collision to do this n-squared, literally n-squared version of it. But if we're going to do this at compile time, what might that look like? Well, now we can start writing all our overloads with just all the different types of shapes, where box with pose and sphere with pose are different types. And overloads are perfectly fine. We don't always need to use a template class or template function to do some of this compile time work. And then I'll use fold expressions for this type of thing and check, is this robot in collision? What I want to do is pass in a tuple with all the different types of shapes, and that'll be our heterogeneous container. And then ultimately, we would just call is robot in collision, and then separate those shapes into their different types. And so you can do a combination of 2 different fold expressions to do something like this, where you kind of combine along the different types. And then the second one you need is combining each shape with each other shape. So I will say that I know this is the n-squared version. There's a lot of duplicate collisions happening. So I'll leave reducing the collision checks to the viewer at home. Thank you guys. Or you guys in your off time later today. Just in summary, hardware companies, not just robotics companies, I think this applies to a lot of companies with developers here. They build and ship code a lot more than they do ship new hardware. So utilizing C++ metaprogramming techniques, we can get the compiler to see and optimize a lot more of your code than your kind of poor, overworked development team. And so I'll say to you, leverage many compile time features to build rich descriptive types. Thank you. I believe you can use the microphone for questions. Yeah.
Hey, Stephen.
Hey.
Great talk. Thank you.
Thank you.
I was hoping you could go back to one of your Godbold examples where you were doing the fold expression for the forward kinematics, and maybe if you could go into that detail just a little bit more.
Yeah, thank you.
For those of us who aren't so good at fold expressions like me.
Sure. So let's see. We're going to call our run forward kinematics with our tuple of joints. This is a heterogeneous types, different types of joints. and then our stood array of positions. That could also be a span. It could be any type. And then there's this trick out there with make index sequence, which will create an index sequence, which is a type that has a bunch of different size t template parameters. And then when you call your fold expression, you make use of the index sequence to expand. So yeah, no, this is, it's a kind of interesting trick to get these things to work because the compiler needs to know how to, along what to expand. And since we're using a tuple, we need to use get to pull the right item out of that tuple. And so we'll use the index into that tuple from the index sequence. And then, so the other part of fold expressions is kind of the operation that you want to do, and then the ... where the magic happens. Where it's just like, yeah, repeat this, but with the next parameter in sequence.
I was curious, have you seen any issues with regard to amount of compile time that it takes to deploy this at scale? Is it something that do you need to worry about a significantly larger scale?
I personally haven't exactly noticed long compile times writing template code. I will say that a lot of the code I have to write runs on embedded platforms, and so I'm not exactly experiencing large compile times. There, I care a lot more about large binary sizes, and that can also be an issue with some, I guess, naive approaches to template metaprogramming. Sometimes your compiler is going to make it a lot smaller because you've given a lot more information. Sometimes you've just told the compiler to duplicate my code in many different ways. And so it does need to be something that you're careful of. But I would hark back to the scenario where you're building a lot, or you're building many times for a robot you're shipping very few times. Like sometimes a long compile time is just suitable to get some of the guarantees that you can provide using those techniques.
Thank you for the talk. It was very interesting. I noticed in the for kinematics example, you had the array of joint positions, which included spots for all the fixed joints, which don't really have a position value.
Yeah.
Is that just you'd fill them in with default values, or would there be a way to avoid having all those intermediate values that don't really, it's just a placeholder in the array?
Absolutely. There's plenty of opportunity for removing some redundancy like that. I think preparing these examples, I was like really trying to get the point across more so than show the best code I can, which I mean, there are some nitpickers here, and I'm sure you zero right in on stuff like that. But you can imagine using techniques like concepts when you're constructor, or your types, or stood enable if, to make sure that the functions that are appropriate are available.
Thank you.
Thank you. Okay, I think that's it. Thank you very much.